Alright, Chapter 5 is pretty straightforward, and it discusses Newton's laws of motion. There are 3 total laws, and these laws really revolve around studying forces, and in particular, how forces move. And the study of moving forces is a field we call dynamics. If we want to very quickly summarize Newton's 3 laws of motion, we can go with the first law, something called the law of inertia. Newton's second law tells us that force is equal to mass times acceleration. And Newton's third law, every force or every action has an equal and an opposite reaction. We'll discuss each of these in more detail in a moment. Before we dive into Newton's laws, we need to talk a little bit about reference frames and the frames where Newton's laws are actually valid. The key thing to remember for Newton's laws to be applicable are that your reference frame has to be inertial. In other words, it can't be accelerating. The word inertial means non-accelerating. The example that I think of when I think of inertial and non-inertial reference frames is a road. I have a road, I have my dotted lines, and I have 2 cars. I have a car traveling in the slow lane, I have a car traveling in the fast lane. This is in a strange world where cars look like potatoes, and on this right-hand lane, this car is traveling usually at a constant velocity. A constant velocity that is usually much slower than the speed that I want to be going at. But since this velocity is constant, I'm not accelerating. This reference frame is not accelerating. It is inertial. This means Newton's laws are valid on my car traveling at my constant velocity. Alternatively, I go to the car that's in the fast lane. He is accelerating, probably talking on his cell phone while he's doing it, and not getting pulled over by the cops. His reference frame would be non-inertial because he is accelerating as he is driving. So key point to remember, inertial reference frames are non-accelerating, and these are the frames of reference where Newton's laws are valid. So Newton's first law, the law of inertia, according to your book, it tells us that in the absence of a net external force, so we can't have outside forces acting on this, a body at rest remains at rest, and a body in motion continues to move at a constant velocity. So objects in motion stay in motion, objects at rest stay in rest, unless there is some kind of net external force. In the world of physics, if I have a car, I turn the car on and I start driving down the road and I take my foot off the accelerator. In the ideal world of physics, the ideal world that we currently live in, this car would keep going forever and ever. In the actual world, this doesn't happen. This doesn't happen because there's some net external force acting on our car. In the case of cars, that net external force is a backwards force. We call that force friction. And we'll be discussing friction in future chapters. And there's another common way to discuss inertia, discuss Newton's first law. It's also discussed in terms of mass resisting change. It's just another way to state Newton's first law. Mass resists change. I think a good example of this is to think of 2 professors. Think of Dr. Bubar and think of Dr. Rimkus. If you were trying to pick a fight with one of us and wanted to knock one of us down, who would you choose? Who would you choose to shove? Would you choose Bubar? Or would you choose Rimkus? If you knew physics, and thanks to Dr. Bubar you do know physics, you want to shove one of these professors, you want to knock them down, the professor you're going to choose is going to be Bubar. Bubar has less mass than Rimkus. If mass resists change, then a bigger mass, somebody like Dr. Rimkus, would be harder to push down and shove than Dr. Bubar. So another way to state Newton's first law, mass resists change, the law of inertia. Newton's second law is the law that should be the most famous law in all of physics. Every student should know this law. It tells us that F is equal to m times a, where F is the force. And notice the little arrow above the F, which means that this is a vector. And this force F is equal to mass, or how much inertia you have, times the acceleration that you have. Each of these quantities has units, the units for mass. Remember, when I put something in brackets, that means that I'm talking about the units. The units of mass are kilograms. The units of acceleration, we should remember, are meters per second squared, which means that the units of force are going to be equal to kilograms times meters divided by seconds squared, and we give this a special name. We call this a Newton, after Newton's second law. So this F equals ma, Newton's second law, the most famous equation in all of physics. Everybody should know this. So we already know what acceleration is. Let's talk a little bit about mass and how we get to mass. Mass is something that we usually measure. If we want to find a standard mass, we compare it to another mass. The approach that I would suggest that is a good way to measure mass is this little device right here. You might remember this from when you were a kid. Maybe you still remember it. If we have two masses, mass 2 and mass 1, on two sides of this device, we're going to call it a teeter-totter. So I take these two masses, and something's going to happen. If mass 1 is greater than mass 2, then it's going to have more gravity, and the teeter-totter is going to kind of bend. It's going to kind of teeter more towards the mass 1 side. And we can use this to determine the relative masses of mass 1 and mass 2. Alternately, if mass 2 is greater than mass 1, then the teeter-totter is going to lead more towards mass 2. This makes physical sense. It's not complicated, but we use this simple principle to figure out how massive something is. We do this by making one of these masses a standard mass. So maybe we compare mass 1 to mass 2, and we use perhaps a kilogram for being mass 2. And if we use a kilogram, then we can figure out the relative mass of mass 1 based on how much this teeter-totter moves. You might have used a device in your other science classes, perhaps in chemistry, called a balance. A balance works in the same way, by comparing two different masses to each other, one unknown mass and a known mass. Often in a physics problem, I have more than one force acting, so I need to think about not just individual forces, but net forces. The net force acting, let's say I have three different forces. My net force would be F1 plus F2 plus F3 dot, dot, dot. And I could expand this to as many forces as I want with the following notation. I have the little sigma from I equals 1 all the way up to n of F with a little n right here. So in this case that we have here, my I's would be equal to 1, 2, and 3, and I get correspondingly F1 plus F2 plus F3. And something that we have to note, something that's very, very important, is this guy right here, this little arrow. This means force is a vector. Since it's a vector, we need to use components. Need components. You have to use the x direction, you have to use the y direction. So you'll be doing a lot of right triangle trigonometry in figuring out these kinds of force problems, because you need to separate into the x and y directions. Continuing onward with the sequence of your book, we need to talk about weight, contact, and the normal force. First, we'll talk a little bit about weight. Let's say I have an object, and I drop it. That object's going to fall. That object is going to have a specific acceleration. The magnitude of that acceleration is going to be the magnitude of a falling body, which, as we all know, or should know by now, is g. I can write Newton's law for this ball that I'm dropping. Newton's law, F is equal to m times a. So the force acting on this ball, the force from gravity, is m times g. We have a side question here. Let's say the ball lands on the ground. Is there still a force acting on it? Does gravity stop acting once you hit the ground? Well, look, Earth is still here. Earth is still exerting a force, still pulling me down. The only thing stopping me from going down is the actual ground that I'm standing on. My force is still acting. I'm still feeling this mass times this gravity. I feel a force that's sticking me to the ground. That force, Fg, the force of gravity, equal to mg, has a special name. We call that weight. And something very important to note about weight is that it can change. I don't mean going on Weight Watchers. What I mean is weight depends on mass and acceleration due to gravity. If the acceleration due to gravity changes, then my weight changes. Think about going to the moon. Think about being an astronaut, floating around up on the moon. The moon has a gravitational constant that's about 1/6 of Earth's gravity. So your weight on the moon would be Fg equals mass times g, gravitational pull of Earth, divided by 6. So your weight on the moon is about 1/6 of your weight on Earth. So weight can change. The variable that won't change is your mass. The only way to change your mass is to go on Weight Watchers. So, weight changes depending on your acceleration due to gravity. Mass, in general, does not change. Your book continues on to talk about balancing forces and a concept called weightlessness. We'll have some demonstrations during lecture, something called the vomit comet, and what I like to call my bucket demo. But in general, what these two demonstrations are going to show us are the concept of weightlessness. So we have some astronaut maybe. He's in his space shuttle, very weird looking space shuttle, and the space shuttle feels the pull of gravity from Earth. So the space shuttle, when it's orbiting around the planet, is actually falling down. Now we've seen videos of astronauts, hopefully, and these astronauts, they're weightless. But their weightlessness is just relative motion, relative to their space shuttle. They're actually falling. The astronaut in the space shuttle is falling, but they're falling with the same acceleration as the space shuttle. So if you accelerate at the same rate as your reference frame, then you are weightless. And we'll see some examples of that during lecture tomorrow. So gravity is a special kind of force. It's something we call a field force, and it works without any two objects touching. Most forces we're going to deal with are something called contact forces. This means you need actual contact for them to work. You need to have some kind of push or some kind of pull. Simple example is of an object sitting on a table. So the simplest example of a contact force I can think of is an object sitting on a table. So we'll draw a nice little red table, and we'll take a box and we'll put it on top of this table. If we could zoom in to this contact point where the box is actually touching the table, and if we looked at the atoms inside of this box and inside of the table, we'd see something. Here's our table surface, here's our little box, and as soon as we put the table on the box, this table actually compresses a little bit, actually moves down. But the table exerts a force on the box, so the box, the atoms inside of the box, actually move up a little bit. Atoms are springy. They feel these forces that are acting, and these forces provide that contact force between our box and our table. We give this a specific name. We know that the box sitting on the table is being pulled down. It's being pulled down by gravity, so it has the force of gravity acting on it. But this table, this springiness between the atoms that pushes back up on the box to prevent it from falling through the table, these springy atoms produce what we call the normal force, F sub n. So normal force has a very specific definition. I like to call it F sub n. Some places you'll see it described as a capital N. I don't like to do that. That seems confusing with newtons. So the definition of the normal force is a force that results from contact. A force from contact. And this exists due to the springiness of atoms, atoms pushing against each other. And the direction of this force is a vector, we need the direction, is always perpendicular to your surface. And we can see that that holds true for this particular case, for this table sitting on, this box sitting on the table. If I draw the angle between my normal force and the surface I'm on, it's a right angle. And this table example leads us naturally into Newton's third law, which tells us that forces come in pairs. We call them action-reaction pairs, and we can write this as a nice succinct equation. The force of one object on another object is equal and opposite to the force of that second object back on that first object. Newton's third law. Every force has an equal and opposite force. So to summarize, Newton's laws. The first law, the law of inertia. Object in motion stays in motion, object at rest stays at rest unless an outside force acts. Newton's second law. The sum of forces acting on an object is equal to the mass times the net acceleration inside that system. And number 3, every force has an equal and opposite force. So when we're working with all these forces, we need a way to describe them. We need a way to identify them, to draw them into pictures. And there's an approach called a free body diagram, where we identify all the forces that are acting on something. And using this free body diagram, we can visualize Newton's 3 laws, and we can solve problems. So how do we do this? How do we draw a free body diagram? Let's go back to our table example. We'll draw a nice little table. And we'll put a box on that table. We need to identify all the forces acting on that box. I know that there's a force of gravity that's pulling my box down, Fg. We also learned that there's a normal force of the table acting up onto the box, the normal force. And this is due to the springiness between the two objects, the atomic springs in the table and the atomic springs inside the box. And one of the most common mistakes people make is assuming that the force of gravity is an action-reaction pair with the normal force. It kind of makes sense. The force of gravity is equal and opposite to the normal force. It seems like that would be the case. But in actuality, gravity pulls down on my box. The box has mass, the earth pulls it down. But the box, like I said, the box does have mass. So that actually means that the box pulls up on the earth. So we need to draw that force in. We have the earth way down here at the bottom that's being pulled up by the box. So this is going to be the force of the box on the earth. And that is the force due to the gravity of the box. We usually don't explicitly write this, and there's no need to do this in future problems, but the force of gravity that we usually talk about, this Fg down here, we usually assume this to mean the force of Earth on the box. But we need to keep in mind that the box does have some gravity and exerts a force on the Earth. And these are your action-reaction pairs due to the contact between, due to the force of gravity, that field force. So we have something similar for our normal force. If we look at our normal force, we drew it as the contact force between the springs inside the table pushing up on our box. We also have a normal force of the box pushing down on the table. Little springs, little atomic springs in our box pushing down on the table. So this is the reaction pair. Action, equal and opposite reaction for the normal forces. Typically, we don't need to worry about these extra forces. This is a subtlety to really understand how forces work. When we're drawing the forces, identifying the forces, the ones we're going to be concerned with are going to be the normal force of the table and the force of gravity. So we want to worry about the force of gravity and the normal force on the table. So to be completely clear, the last slide was talking about the subtle points of a free body diagram. Here we get into the practical points. the forces that make more sense, that are really easy to see. We have the force of gravity acting on our box, pulling it down. Force of gravity. And we also have the force of the table on the box acting up, the normal force. These are the two primary forces that are acting, and we can solve all problems with these two forces without worrying about the action-reaction pairs, the subtlety of the box actually having a force pulling the Earth up, and the subtlety of the box actually having a normal force down on the table. So we'll not just have contact forces, normal forces, we also have something called tension. Tension is how taut a cable is. So let's say I have a cable and I have a box hanging from the end of my cable. This box exerts a force on my cable, and the cable exerts a force on the box. To find the direction of the tension in the cable, the tension is the force, the tautness inside this rope, inside this cable. You can think of it as the tautness, how tightly pulled this cable is. And tension always acts in the direction that the cable is. So tension in this cable would be acting up along the cable direction. To get a handle on this, you really need to look at and study closely examples 6, 7, and 8 in your textbook. Also example number 11 and the extra practice video problem that I'll be posting. So let's get to solving some problems involving motion with a constant force. So this means that the acceleration of our objects isn't changing. It can have an acceleration, but the acceleration is not changing. So we look at Newton's second law, sum of forces is equal to mass times acceleration. As long as this A is constant, we'll be able to use the four 1D motion equations that we should all definitely be very, very good with by now. And we can use them in this case, this example that your book describes of a man pushing down on a box. Here's a man, his head, very short legs, very long arms, and he's pushing down on this box. So this is the problem we're going to discuss. This box is moving forward. It's moving forward with an acceleration of A. And the first step in these force problems, first thing we want to do is to draw a free body diagram. So I'm going to redraw my little situation. We have our guy standing here, and he's pushing down. He's pushing down on a box. We know he's applying some kind of force, and we know that the box is accelerating. We want to identify all the forces, so we need to identify a good reference frame. We're going to use our standard one that we're used to, the X and Y axes. We have positive going to the right, positive going up. To draw our free body diagram, all we need to do is really worry about what's going on with this box. So what forces are acting on my box? Usually, a good frame of reference, a good starting off point, is to identify all the forces acting at the center of the box. What is the effect of the forces at the center of the box? We know the push is pushing our box downward. That's the force of our push. And from the very beginning, we know that this is at some angle to the x-axis, some angle called theta. We know we have gravity acting on our box. Gravity is pushing our box down. And we know we have a normal force. We have a force between the table and box that's acting up, preventing the box from falling through the table. So this right here is your free body diagram. You don't have to worry about the details of the person, don't have to worry about the floor. All you need to do is identify and label all the forces that are acting and the directions. Because we need to remember, force is a vector. So these directions are going to matter. So we have our free body diagram. We have all of our forces. We have one force acting up in the y direction, another force acting down in the y direction, and then we have a force of a push that's acting at an angle. So it's got a little bit in the x and a little bit in the y. We should be used to this by now. Forces acting in different directions, anything acting in different directions, think like projectiles, we separate it into the x direction and into the y direction. And we can use Newton's law. Newton's second law, the sum of forces in the x direction, is going to be equal to mass times the net acceleration in the x direction. For this particular box, the sum of forces in the x direction is equal to the force of push acting in just the x direction. We know that we have some little bit of F push that's acting entirely in the x direction. And that force is the only one I see acting in the x direction. So that's going to be equal to the mass times my acceleration in the x. I can look in my y direction. The sum of the forces acting in the y direction is going to be equal to the mass times the acceleration in the y direction. I look at my forces. I have the normal force. The normal force is acting up. I can see the normal force acting up entirely in the y direction. And then I have gravity acting down. The force of gravity acting down. So I have to subtract it off. It's acting in the opposite direction to my normal force. But then I also have this force from my push in the y direction. It has a y component. I can see the x component. I can also see the y component, pushing it down, acting in the same direction as the force of gravity, so I subtract it off. That's going to be equal to the mass times the acceleration in the y direction. But if we look closely, the only acceleration that we have is the block moving in the x direction. It's moving along the floor, it's not bouncing up and down as it's moving, so the acceleration in the y direction is 0. So we can write our forces Fn minus Fg minus Fpy is all equal to 0. And that is the general approach to writing a free body diagram. You identify your forces, make sure you identify the directions, maybe some in the y direction, maybe some at an angle, and you have to then break them up into what's happening in the x and the y directions, since force is a vector. Write the sum of forces in the x direction. That's going to be equal to the mass times the acceleration in the x direction. Write the sum of forces in the y direction, equal to the mass times the acceleration in the y direction. So this projectile approach of separating directions works for force problems as well.